In this video, I hope to provide everybody perhaps a greater understanding of writing out electron configurations and exactly what they represent within an atom. So we know that within any given element we have a certain number of protons and electrons, and what electron configurations really focus on is where those electrons are placed within that atom. So essentially, as we've already talked about in the past, we have certain energy levels. I've numbered them here, 1, 2, 3, 4, 5, 6, 7, and the key point to understand here is that within each one of these energy levels, we're going to have different orbitals. We're going to have the s orbital, the p orbital, the d orbital, and the f orbital, all within these different energy levels over here. And so what I really want us to get a better understanding of is exactly how many electrons go into which orbital and in which order they actually go into the orbital. So we know that the s orbital, can house exactly 2 electrons, p can hold 6, 10 can hold 10 electrons, and f, which is the largest orbital, can hold 14 electrons. So I think that the best way to really get an understanding of how this is worked out is to just do an example. So how about we write out the electron configuration for aluminum? Okay, we know that aluminum is the 13th element on the periodic table. It has 13 electrons. So let's just try to work this out. I've drawn diagonal slashes, and that's probably the best way to remember the order in which electrons go into the different orbitals. So we know that first we're going to go through 1s, then we're going to go through 2s, and then we're going to go through 2p and 3s, and proceed on to 3p and 4s, and so on and so forth. But for this, because it only has 13 electrons, we're going to finish off pretty quickly, so we'll probably only need this half of this table I've set up over here. So we know that this table over here tells us to start with 1s, and we know that s can house 2 electrons. So we're going to start out with 1s, and we know that we can have 2 electrons in it, so we're just going to write the superscripted 2 to signify that we have 2 electrons within this orbital, so 1s2. Next, it's telling us to go to 2s. We know that s still can only house 2 electrons within this energy level, so it's going to be 2s, 2s, and again we have 2 electrons within it that we're using. Now let's see how many we've gone. We have 2 electrons here, we have 2 electrons here, that's 4 electrons. We still have 9 to go. So now it says, okay, go 1s, go 2s, we've already done that. Now it says go to 2p and then go to 3s. So first we're going to start off with 2p. 2p we could have 6 electrons. That's fine because we still have 9 that we need to get to. So we're going to write down 2p6. So now we've gone 2 electrons, 4 electrons, 10 electrons. We have 3 electrons to go. So now it's telling us to go to 3s. 3s, the s orbital can still only house 2 electrons, so we're going to write 3s2. Now it's telling us to go to 3p. 3p at its maximum can house 6 electrons, but because we've gone 2, 4, 10, 12, we only need 1 more. So we could just write 3p, and because we only need 1 more electron to fit within this orbital and this energy level over here, we're going to write 3p1. So this is the electron configuration for aluminum. Another example we could do is let's do one that's higher up on the periodic table. We could do bromine. Bromine is the 35th element on the periodic table, so that means it has, of course, 35 electrons. So right now, I'm just going to repeat the process that I carried out over here. So we know that we're going to go to 1s first. 1s can house 2 electrons. 2s can house 2 electrons. 2s2. 2p can now house 6. 2p6. 3s, we go back down to the s orbital because we're always trying to conserve energy here. 3s can hold 2 electrons, so 3s2. So now I'm just going to do a little quick check. Gone 2, 4, 10, 12. Okay, so 35 minus 12, we still have 23 electrons that we need to go. Now it's telling us to go to 3p. Well, 3p can house 6 electrons, so 3p subscripted 6. Now go back down to the s orbital. S can only house 2, so now we're going to do 4s2. 2, 4, 10, 12, 18, 20. We still have 15 more electrons that we need to go. Alright, so now we're going to 4s. So now something interesting happens. Now the diagonal slashes now tell us to go to 3d. D is a new orbital, and D can now house 10 electrons. So now we could go straight to 3d, and then write the subscripted the superscripted 10. So now we've gone 2, 4, 10, 12, 18, 20, 30. We now have 5 to go. Now it's telling us to go back down to the 4p. Well, p can house 6, except we only need 5 more to go. So we're still going to have the 4p. These final electrons are still going to be located within this orbital, except now we only have 5 to go, so it's still going to be 4p5. And we're done.